Earth is about to be blasted by a 700,000 km/h stream of charged particles from a rare trans-equatorial coronal hole, right as an interstellar comet, 3I/Atlas, vanishes behind the Sun without warning. Experts call this a perfect coupling event. The magnetic gateway is wide open, and geomagnetic storms can ignite with almost no resistance. At the same moment, a sudden spike in powerful earthquakes leaves scientists arguing over coincidence versus cause. Some dismiss any connection, others warn we're watching a cosmic pattern unfold. The official story insists nothing links these events, but 3I/Atlas is doing something with our Sun, and when it reappears, what we find may rewrite the rules. The first question is, what does a solar storm of this scale really mean for Earth? A coronal hole is not a hole in the Sun, but a region where the solar atmosphere thins and the magnetic field lines stretch out, unanchored, into space. Most of the Sun's surface locks its magnetic fields into tight, looping arcs, trapping hot plasma. But inside a coronal hole, those lines open wide, like a gate left ajar, letting charged particles escape at extraordinary speeds. On satellite images, these regions appear as dark, yawning gaps that can span thousands of kilometers, sometimes crossing from one solar hemisphere to the other. When a coronal hole stretches across the Sun's equator, it becomes a trans-equatorial highway for solar wind, connecting north and south and channeling energy directly toward the planets. The October 2025 event began with SDO/AIA imaging, which captured an unusually broad unipolar coronal hole bridging the Sun's hemispheres. Magnetograms confirmed the field was negative and open, a configuration that's rare outside of solar minimum. This open structure allowed a high-speed stream, clocked at up to 700 km/s, to break free and race through the inner solar system. Space weather physicist Dr. Timothy Skov describes these regions as magnetic exhaust vents, where the Sun's plasma doesn't just simmer, it surges outward, unchecked. The direction and polarity of this outflow matter. When the Sun's open field aims directly at Earth, the planet's own magnetic shield is forced to contend with a relentless, focused blast. This is the physical mechanism behind the so-called perfect coupling setup. The magnetic door is open, the wind is fast, and Earth stands directly in the path. What happens next depends on how these fields interact. Solar wind doesn't simply brush past Earth. When a high-speed stream arrives, especially one clocked at 700 km/s, the planet's magnetic shield is forced into a direct contest. The real drama unfolds at the boundary where solar and terrestrial fields collide. Here, the interplanetary magnetic field, or IMF, acts as the key. In October 2025, the IMF pointed sharply southward, holding steady near -12 nanotesla. That orientation is critical because Earth's own field points north. Opposite directions mean the fields can snap together, a process called magnetic reconnection. This is the gateway for solar energy to pour into the magnetosphere. They translate to real-world effects, power grid fluctuations, satellite drag, and most visibly, auroras stretching far beyond their usual haunts. On the night of October 12th, curtains of light rippled as far south as Michigan and Maine, a direct consequence of the efficient coupling between Sun and Earth. The result? A geomagnetic system primed for action, where even a moderate solar wind can trigger a chain reaction across the planet's upper atmosphere. Each spike in velocity, each shift in polarity, sends a ripple through the global electrical environment, setting the stage for questions that reach well beyond the magnetosphere. 3. I/Atlas is not just another icy wanderer. It's the third interstellar object ever confirmed, and its chemistry reads like a challenge to everything we thought we knew about comets. Most comets in our solar system are dominated by water vapor, but 3I/Atlas is different. Its coma is fueled by carbon dioxide, outgassing at rates nearly 8 times higher than water. That's a signature more typical of the frozen outskirts beyond Neptune than anything born in our own backyard. Spectroscopy from ground and space telescopes paints a picture of a nucleus smaller than a kilometer, yet active enough to shed material at a rate of up to 4 kilograms per second. Even at distances of 4 or 5 astronomical units from the Sun, it was already producing a visible coma, a cloud of gas and dust that forms when sunlight heats the nucleus. The dust itself tells another story. Instead of the fine grains that create long, glowing tails, 3I/Atlas seems to favor larger, heavier particles. The result is a faint, asymmetric haze rather than a dramatic streamer. Its rotation period, measured at just over 16 hours, matches the restless, tumbling motion seen in other active comets, but the details of its surface chemistry, rich in organics with a high carbon dioxide to water ratio, set it apart. As one SDO mission scientist put it, "This is a messenger from another star system, carrying a recipe we've never tasted." The uniqueness of 3I/Atlas isn't just a curiosity. It's a test case for how interstellar chemistry responds to the Sun's heat and what secrets might be revealed as it rounds perihelion. A cluster of magnitude 7 earthquakes rattled seismographs across the Pacific Rim in the same week that 3I/Atlas disappeared behind the Sun and the solar wind battered Earth's magnetic field. The timing fueled a wave of online theories, some claiming the Sun's outburst or the comet's passage had triggered the seismic spike. Yet, when examined against the global baseline, the numbers tell a different story. According to NOAA's Space Weather Prediction Center, Earth averages around 15 magnitude 7 or higher quakes each year. This week's activity, while dramatic, falls well within statistical expectations. No mainstream seismologist accepts a direct, physical link between solar wind and tectonic plates. Meta-analyses of decades of data find no reliable pattern connecting solar storms to earthquake timing. Still, speculation persists. Fringe theories invoke ionospheric coupling or subtle changes in Earth's rotation, but these remain unproven and outside accepted geophysics. As NOAA forecaster, Michael Fulmer explains, the burden of proof lies with those claiming a connection. Without a reproducible mechanism or clear statistical anomaly, science treats these events as coincidence, not causation. The debate isn't just academic, it sets the standard for what counts as evidence when extraordinary claims collide with data. 4 distinct outcomes wait on the far side of the Sun, each with a signature that reveals itself in the data before the comet itself comes into view. The first is the simplest. 3I/Atlas survives perihelion intact. In this case, the comet reappears with a brightness curve that matches pre-conjunction predictions, steady, perhaps faint, but unmistakably on track. Its coma remains compact, and no sudden changes ripple through its light. This is the outcome most comet scientists expect, but it's also the least dramatic. The second possibility is fragmentation. Here, the story shifts in an instant. Spacecraft coronagraphs, SOHOs, LASCO C3, Stereo-ASHY-1, Parker Solar Probes WIS-PR would catch a sudden jump in brightness, often by more than a full magnitude. Instead of a single point, the images might reveal a string of fragments, a train of nuclei stretching along the comet's path. The dust cloud expands, the coma blurs, and the tail may split or kink. Past cases like C/2011, W3 Lovejoy, and C/2012, S1 ISON showed these signs: abrupt brightening, bifurcated tails, and multiple points of light where only one belonged. A sodium tail, rare, bright, and yellow, can flare up in the wake of violent disruption captured in LASCO's sensitive filters. A third scenario is dormancy. The comet emerges, but its activity has collapsed. The coma shrinks, the tail fades, and the nucleus appears almost stellar, faint, unresolved, and possibly lost in the solar glare. The brightness curve drops below forecast, and ground-based telescopes may struggle to recover the object at all. This outcome mimics what happened to several faint sun grazers. A return so quiet it's nearly invisible, with only a sharp-eyed instrument scientist flagging the anomaly in the data. The final, most dramatic fate is total disintegration. In this case, the comet simply fails to reappear. No trace in the coronagraphs, no fragments, no outburst, just a silent gap where the nucleus should be. The only evidence is a ghostly dust trail or a brief, unanticipated spike in brightness as the nucleus vanishes. Each of these outcomes leaves a fingerprint in the data: a brightness jump, a sodium flare, a train of fragments, or a vanishing act. When the images drop, these are the signs to watch for. Recovery begins with a single image: Soho's LASCO C3 coronagraph, uploading its latest frame to the Quick Look archive. Every 12 minutes, a new snapshot appears, and comet hunters around the world scrutinize each pixel for signs of 3IAtlas. The first hint could be a faint point of light, a sudden brightening, or a subtle distortion in the solar background. When the data stream shows anything unusual, an unexpected spike, a new fragment, a sodium flare, alerts ripple through the observing community. Robotic telescopes take over next. Facilities like Zwicky Transient Facility and Pan-STARRS are programmed to sweep the region as soon as 3IAtlas moves far enough from the sun's glare. These telescopes cover enormous swaths of sky in a single exposure, capturing anything that stands out from the background stars. Each night, their automated routines compare fresh images against star catalogs, flagging any object that shifts position or changes brightness. If a candidate appears, photometry protocols kick in. Observers measure its light in multiple filters, logging the magnitude and color in real time. A steady, predictable rise supports the case for an intact comet. A sudden jump suggests fragmentation or outburst. Amateur astronomers play a critical role in this relay. With the right timing and a modest telescope, backyard observers can confirm or challenge early detections. Their images, uploaded within hours, add redundancy and extend the search into gaps between professional surveys. Every successful sighting is logged with precise coordinates and brightness, building a chain of evidence that tracks the comet's recovery. This coordinated approach, spacecraft triggers, robotic sweeps, and human vigilance, forms the backbone of post-conjunction search. The same playbook applies to any faint, fast-moving target, and those skills will soon come into play for the next visible comet in the sky. For now, every telescope, automated or handheld, is pointed at the horizon, waiting for 3IAtlas to break the silence. Every clear morning for the next 2 weeks, a comet waits in the east, brighter than most city dwellers ever realize, yet easy to miss if you don't know where to look. Comet C/2025 A6, better known as Lemon, now glides through the constellation Cancer, rising before dawn and offering a rare chance for anyone with a pair of binoculars to catch a living piece of the solar system in motion. No telescope required. Just step outside an hour or two before sunrise, find a spot with a clear view low to the eastern horizon, and scan just above the familiar stars of Cancer. Lemon's predicted magnitude hovers between 4 and 5, bright enough to stand out as a fuzzy, diffuse patch, but not so bright it leaps out to the naked eye. Under dark skies, the coma may look like a soft, round cloud, with a hint of a tail stretching away from the sun. The tail is short, spanning maybe half a degree, and often lost in the morning twilight, but binoculars reveal its subtle glow. Timing matters. The next 14 mornings are peak, as Lemon climbs higher each day and the moon stays out of the way. By mid-November, the comet will fade and slip closer to the sun's glare, making this window the best shot for a first-time comet observer. A simple 7x50 or 10x50 binocular, anything you take to a ball game, will do the job. Even in suburban skies, the comet is visible if you know exactly where to look. Many amateur sky watchers keep a star chart handy, or use a phone app to pinpoint its position. Some set alarms for 4:30 a.m., grab a thermos, and step into the backyard before the world wakes up. For those who catch it, Lemon is more than a smudge of light. It's a practice run for bigger cosmic events to come, a way to tune your eyes to faint details, learn the rhythm of the sky, and join a community that chases these fleeting visitors across the heavens. Every observation, whether it's a quick glance or a carefully logged brightness estimate, adds to the global record. The skills you build now, reading the sky, tracking a moving target, knowing when to look, will serve you well when the next comet or interstellar object appears. For now, the instructions are simple. Set your alarm, grab your binoculars, and look east. The solar system is putting on a show, and the ticket is free. Long after Lemon has faded from the morning sky, the calendar of cosmic events stays crowded. Another comet, C/2020 R2 Swan, is already drawing attention for reasons that go beyond simple brightness. In early 2026, Swan is expected to reach binocular visibility, but what sets it apart is the ultraviolet glow enveloping its head. A hydrogen corona, first detected by the Swan instrument aboard the European Space Agency's SOHO spacecraft. This shroud of hydrogen, invisible to human eyes but blazing in the ultraviolet, acts as a signpost for cometary chemistry. Its discovery rewrote the playbook for how astronomers trace the earliest stages of water breakdown in a comet's coma. By comparing the light curves of Swan and Lemon, how each comet brightens and fades over time, researchers can tease out the hidden physics that govern outgassing, fragmentation, and the slow erosion of icy bodies under solar heat. The twin tracks these comets leave in the data will serve as templates for interpreting the behavior of future, more distant visitors. But the sky's agenda doesn't end with comets. 5 milestone dates now stand out as waypoints for anyone tracking the solar system's restless pace. Late October through early November 2025 marks the recovery window for 3IAtlas, when telescopes worldwide will hunt for its return from behind the Sun. On April 13, 2029, asteroid Apophis will pass so close to Earth that it will dip below the altitude of geostationary satellites, a flyby within 32,000 kilometers, visible to the naked eye over parts of Europe and Asia. September 20, 2040 brings a planetary alignment, a so-called parade, when Mercury, Venus, Mars, Jupiter, and Saturn will all cluster on one side of the Sun, offering a rare tableau for astronomers and skywatchers alike. Looking farther out, the year 2060 carries a speculative promise. The possible arrival of a megacomet, flagged in current surveys as a distant, slow-moving object with the potential to rival the great comets of the past. And in 2177, Pluto will complete its first full orbit since its discovery in 1930. A slow, stately lap that frames the entire modern era of planetary science. Each of these dates is more than a curiosity. They are reminders that the solar system is a living laboratory, constantly shifting, always offering new puzzles to solve. The sky's calendar is open, and for anyone willing to look up, the list of appointments is only getting longer. In late September 2025, a trans-equatorial coronal hole unleashed a 700 km/s solar wind stream, driving geomagnetic storms and auroras as far south as Michigan. At the same time, interstellar comet 3I/Atlas vanished behind the Sun, its fate unknown until late October. While some noted a spike in magnitude 7 earthquakes, seismology records confirm that such clusters occur about 15 times per year, with no proven link to solar activity. Spacecraft including SOHO, Stereo, and Parker Solar Probe captured the critical conjunction window, but their data leave open whether 3I/Atlas survived, fragmented, or disintegrated. As of now, no classified files address the comet's outcome. What is certain? The interplay between solar physics, planetary defense, and citizen science is ongoing. The next chapter begins in late October, when ground telescopes will search for 3IAtlas's return. In the words of mission scientist Dr. Tamitha Skov, the Sun's story is written in data, not guesses.